Before applying mathematical processing to a physical signal like sound, it must be digitized. The continuous physical wave is captured, sampled, and snaps into a strict grid of discrete numbers stored in memory. The fundamental building block of this digital environment is the delta function. It is strictly binary, a single sample with an amplitude of exactly 1 at position 0 and an amplitude of 0 everywhere else. Suppose we have an unknown digital filter, a black box. To understand exactly how it alters data, we need a way to completely define its behavior. If we feed that single delta function into the unknown system, the output we get is called the impulse response, or filter kernel. Because we are dealing with a linear time-invariant, or LTI system, knowing this single reaction to a delta function gives us total predictive power. If we know the impulse response, we can perfectly calculate how the system will react to any complex input signal. Here we see the mathematical engine that performs this calculation, the discrete convolution sum. The output signal, y of n, is the sum of the impulse response, h of j, multiplied by the input signal, x of n minus j. Convolution functions as the definitive physics equation governing how digital information propagates through an LTI system. To understand how convolution actually works, we can look at it from two perspectives. The first is physical intuition, the input side algorithm. This series of graphs shows how every individual sample in the input signal, x of I, acts as a scaling factor. It multiplies the entire impulse response kernel and projects that scaled copy forward in time to its own position. Here we see the final summation result. The output signal, y of n, is the superposition, the stacking up and adding together of all those individual scaled and shifted projections. While that explains the physics, writing efficient software requires a different perspective, the output side algorithm. Instead of projecting forward, code calculates one discrete output point at a time by looking backward at the inputs. This diagram illustrates the convolution machine process. To calculate a specific point, we align the impulse response kernel over a window of the input signal, multiplying the overlapping samples and summing them up. Notice the critical mechanical step here. The impulse response array must be reversed or flipped left to right relative to the input before we multiply and sum. This accounts for the n minus j term in the formula. We slide this flipped kernel across the input to calculate subsequent output points, like y of 8 and y of 11, continuing until the kernel has completely passed the input signal. The input side perspective shows us the physical reality of the signal, but this flipped output side perspective dictates exactly how to write the software loop to calculate it. Engineers do not rewrite the convolution algorithm to achieve different audio or data effects. They simply change the geometric shape of the impulse response array. Leaving the delta function at 0 creates an identity filter that passes the signal unchanged. Scaling its amplitude creates volume amplification, and shifting it along the horizontal axis creates a temporal delay. Here is the formula for an echo kernel. By summing a primary delta function with a scaled, delayed copy of itself, the convolution physically duplicates the original signal and adds a quieter, delayed echo. Kernels can also perform operations akin to discrete calculus. A first difference kernel calculates the instantaneous derivative to return the exact slope of a signal. This kernel features a positive spike at 0 and a negative spike at position 1. As it slides across the input, it continuously subtracts the previous sample from the current one, isolating the exact rate of change. Every digital effect, from basic volume control to complex edge detection in image processing, is ultimately just a specific geometric shape residing in the impulse response array. When multiple linear time-invariant systems are connected, they follow specific mathematical rules. Cascaded systems operate associatively. If a signal passes through 3 sequential filters, you can convolve those 3 impulse responses into a single master kernel beforehand, saving significant processing power. Parallel systems operate distributively. If a signal splits into 2 different filters that are later combined, you can simply add their impulse responses together into one array. This ability to cascade systems reveals a deeper statistical behavior. Because cascading systems is mathematically equivalent to convolving their kernels, we see the emergence of the Central Limit Theorem. When any arbitrary pulse shape is convolved with itself over multiple passes, it inevitably transforms into a perfect, symmetrical Gaussian bell curve. The precise widening of this emergent curve is governed by this equation, where the final standard deviation equals the original standard deviation multiplied by the square root of the number of convolutions. Through these interactions, convolution imposes fundamental statistical laws of smoothing on complex digital networks. In software engineering, there is frequent confusion over whether to call a convolution function or a cross-correlation function. The mathematical difference comes down to a single, rigorous mechanical step. On the left, convolution slides a flipped kernel across the data. On the right, cross-correlation slides the kernel exactly as it is, without flipping it. Conceptually, convolution modifies an input signal to create something new. Correlation measures the similarity between two existing signals. We see correlation applied in matched filtering, used on vintage radar consoles like this one, where a known target shape is buried inside chaotic background noise. As the unflipped correlation kernel slides across the data, it produces a massive mathematical peak exactly when it aligns with the hidden target shape. The rule of thumb is straightforward. Use convolution to filter a signal, and use correlation to search a signal. Computing time-domain convolution on actual silicon hardware runs into harsh physical limits. Because of the sliding window process, software executes nested loops. An outer loop steps through every time sample, while an inner loop runs through every filter element. This algorithmic scaling is strictly O of n times m, multiplying exponentially as arrays grow. For long, high-resolution audio or radio signals, this exacts an unacceptable computational latency. A slow filter creates lag. To combat this, engineers invented digital signal processors, dedicated hardware chips optimized specifically to accelerate this heavy multiply and accumulate burden. But eventually, high-resolution arrays become too massive for even advanced DSPs to calculate efficiently in the time domain. To break this O of n squared speed limit, engineers moved to FFT convolution, where the sliding window is bypassed in favor of pointwise multiplication in the frequency domain.